So, welcome back to the afternoon session. I'm Makoto Tsubota, chairing this session. The first speaker of this session is Professor Lauro Tomio. The title is Josephson-type atom number oscillations in tunable spin-orbit coupled VC with time-dependent Raman frequency. Why not start?
Hello. Thank you very much for the invitation to present this talk. I think to Hussein and Pagnato and people that are organizing this meeting. Okay, so I'm going to talk about some collaboration that I have in the Institute of Physics Theory, together also with people from USP, like Arnaldo, about Josephson-type atom number oscillation in tunable spin orbit coupled back with time-dependent Raman frequency. So first, I'm just doing some introductory remarks, and after I talk about spin orbit coupled back with the equal Rashbach-Drexel contribution, time-modulated Raman frequency, and internal Josephson oscillation. Next, I'll talk about two regions where we have regular or striped solitons, and high-frequency modulation also at the end, and conclusion. Okay, this is a collaboration, as I told before, with Professor Arnaldo Gamal from USP, also Mariana Bertica from Universidade Federal do ABC, in Santo André here, and Fatkula Abdullaev, that's one of our frequent visitors in our institute here, and also in UF ABC. Okay, this work is mainly also published now in the Physics Review A also. Okay, first I resume here what I'm going to talk is the existence and dynamics of solitons in quasi one-dimensional Bose-Einstein condensation with spin-orbit coupling and attractive two-body interaction are described by two coupled atomic pseudo-spin components with slowly and varying time-dependent Raman frequency. By varying this Raman frequency, linear in time, ordinary non-linear bright solitons can be converted to striped solitons and vice versa. So internal Josephson oscillation between atom numbers and of the coupled system and center of mass motion are studied considering a parametric resonance mechanism proposed by to control the solitons. So in the limit of high frequency, the system is described by some time averaged Gross-Pitaevsky formalism with renormalized nonlinear and spin orbit coupling parameters, and with modified also phase-dependent nonlinearities. The lower limits of this parameter Raman frequency to obtain stable solid are also verified. So this I show also the formalism that we are using here is about a spin orbit coupled Bose-Einstein condensation with equal Rashbach-Drexel contribution. The spin orbit coupled back with equal contribution for the spin orbit coupled tables is considered. The harmonic trap in our case is such that just to go to the one-dimensional nonlinear Schrödinger equation, but that one direction is much smaller than the perpendicular direction of the frequency, of the trap frequency. So our units of energy and length are that here, that's the dimensions, that the frequency in terms of this frequency, perpendicular frequency, with m is the mass of both atomic components. So with this we can obtain a dimensionless spin orbit formalism for the two-wave couplet here. Okay, so here you have the spin orbit coupling term. This is trap. Harmonic trap, and here is the Raman frequency, and the sigmas here are Pauli matrix, and the trap I'm going to put almost equal 0 at the end here, just to bring to the condition of to have the soliton solution. So KL is the strength of the spin orbit coupling, and Raman frequency is time dependent there, with beta and gamma, the scattering length ratio. So beta is the interspace divided by intraspace, and gamma is the the ratio between the two intra-species components. Mostly of the work I'm taking gamma equal 1, so the most important parameter sometimes is beta, at least in this work. No? And also we are considered additive to body interactions, such that we have an overall minus for the nonlinear part. So from the symmetry of the coupled equation, if I take gamma equal 1, we can extract a simple relation also between the two components. So for a given KL, we are identifying the solutions, one related to the other in this way. So depends on the KL, just change the signal. I can go from V to U directly. And for the constant Raman frequency, omega t equal omega 0, a linear expression can be derived for plane wave with momentum k. So, and uv can be written that way as a plane wave. And in that case, this energy parameter here, we have omega k as a function of k plus or minus kl from the spin orbit and k squared plus omega 0. So this is plot as a function of k, where two regions I can identify, region 1 and region 2, according to the choice of these two parameters that I have, the spin orbit coupling and also the Raman frequency. So a linear spectrum can be drawn using that. The energy dispersion for omega plus and omega minus are shown. That's just identify the two regions that I have. One is for KL squared, smaller than omega 0, the upper panel. And second region is when KL is larger than omega 0, lower panel. In both panels, the dot dashed and dot lines indicate the extremes, with the minima of omega plus being at omega 0, the center, in both cases, and the minimum of omega minus are at k omega minus 0 in region 1, and plus minus, so deviates from the center here, where I have a local maximum here, in the region 2. In that case, the k0 can be identified, this minimum, as KL squared minus omega 0 squared divided by KL squared. That's the position of these two minima that I obtained. So this is already verified by Achilles et al. In a physical review letter that bright solids are obtained in region 1. However, for region 2, the solution are striped type of soliton, of bright soliton. So next we are exemplify the kind of solutions in both regions for constant and also for linearly time-varying Raman frequencies. This, for example, if I have just, for now I take this omega constant, but take in different times now. So a soliton profile is shown for KL equal 8, from beta equal 1, gamma equal 1 also, is the Raman frequency varying as shown adiabatically. So generated as a stripe in region 2 is converted to a regular soliton to region 1 and after back inverting the time variation. So here I have a striped solid at time equals 0 and I'm increasing here and I am modifying the format of these solitons by just this parameter. And now increasing more this omega here, I can go back and inverting the time, get back to the striped type of soliton. So they are generating one region 2, and I'm going back to the same region 2 at the end, passing to region 1. So now I introduce also the time of variation, modulated Raman frequency and internal Josephson oscillation. So for time modulated Raman frequency, and the influence of time varying Raman frequency on the oscillation in atomic population, this internal Josephson effect that we call is the atomic population that I transfer from one component to the other component, the densities. No? So we study in region 1 and region 2. So interesting because periodic modulation of Raman frequency may lead to resonant responses. of Bose-Einstein condensation solitons with the spin-orbit coupling. So these phenomena can occur for imbalanced populations, which are produced initially with different phases. In both the cases of region 1, when omega 0 is larger than KL squared, and in region 2, when this is smaller than KL squared, we first implement the oscillation for constant omega 0. Next, we introduce a phase between component and perform the time evolution. So that is the function that, that we have for the Raman frequency. We put a cosine omega t here. That's the frequency of the oscillation with amplitude equal omega 1. Where omega 1 is the amplitude, so the other is the frequency of this oscillation that they are introducing. So different regimes are possible, considering the frequency slow, resonant, or rapid modulation. Depend on this frequency to be much smaller, the half order of omega 0, or rapid. First, we are concerned with the regime where we can have a resonant response. Therefore, we assume omega 1 much smaller than omega 0, so the amplitude very small compared with the omega 0. Just to identify where we can have some resonant effect. So the other regime with high frequency and large amplitudes, omega 1, we have considered in the final part of our work. So full numerical simulation were complemented by variational approach, also in region 1, where KL squared is smaller than omega 0, and the regular soliton solutions are obtained. In this case, the interference, the effect on the oscillation due to the omega t was studied with these ansatz now. So this is mostly for region 1, where the variational approach works better, and also we can identify with this variational approach more or less the parameter for a full numerical calculation. So AI, these are parameters, A, X0, and Ka, and that the phase are time-dependent parameters. So with the corresponding Lagrangian and density using the Euler-Lagrange equation, we have a set of equations to obtain for the parameters, considering small values for the spin-orbit carbonyl strength, KL, as compared with omega 0. The system is reduced to the following one here. For the phi and z, the z is the difference between n1 and n2, where n is the total number of particles. And phi is the difference of the phases. And omega is a parameter that depends on beta, but one can also check here, because if beta equals 1, this parameter goes to 0 in some case, some limiting case. So the coupled equation describes the internal Joseph oscillation of atomic population between the pseudo-spin components. So for a constant omega, these oscillations have been studied by Zhang et al. Also in 2012, and also there are some works that we cite there. In 2018, it appeared when investigated the macroscopic quantum tunneling obtained in a double well potential with a barrier between the wells with constant height. So at some modulating frequencies, parametric resonance can occur. In region 1, where we have bright type soliton, the full numerical results are fully compatible with our variational approach. However, for the region 2, where we have striped type soliton, the coupled system is not so amenable to a simplified variational approach, which can provide only rough estimates at some limiting condition. So our study relies mostly in full numerical simulation for the region 2, which provide convergent results with high numerical accuracy. Most of this numerical calculation was done by Arnaldo Gamalho and also by Marijana Bertka. So region 1, where I have regular soliton. I can show some results here. The result with constant omega 0. So the frequency of the free oscillation is given by that omega j, that equal to omega 0 there, for beta equal 1. For beta equal 1, I have that lambda equals 0. No? So the dependence of the oscillation on initial phase is verified for the difference between N1 and N2. in region 1 with omega 0 equal 80, this case here, and 20, the second case. The results are given here for different initial phases, pi by 8, pi by 4, and pi by 2, with KL equal 4 and gamma and beta equal 1. So this shows how the initial phase affects the amplitude, however, does not affect the frequency as shown. That is of the order of 2 omega 0. So the effect mostly is just the amplitude. So it's better to take some phase that's larger to have a larger amplitude in the initial. So the density plots for soliton profiles correspond to the lower panel of previous figure with omega 0 equal 20 is here, with U square is the upper panels for the first component. The second component is just V that you see that are in phase here, and here is when I combine both solutions for the density of first and second component. And obtain in time from 0 to 1 here, and the position X there. So in region 1, well, I can see now introducing that time-dependent omega 1 with omega 1 much smaller than omega 0, such that I can identify resonance interference in atom number oscillation. So in this case, we are verified for a few values of the parameter beta. That's the ratio between the A's, the A12 divided by A11, the scattering length, for KL equal 8, gamma equal 1. Here one can see also for beta equal 0 is this here that's slightly visible here in this case. And this is the other case here with beta equal 0.5. And after the increase, this goes more or less flat here. And if I go to large values, I think it's go more or less constant near 0.40. But there you can see also a large influence. For omega equal 2 omega 0. Because this omega equal to omega 0 is dictated by some variational approach before. Yeah. And delta t is then up to the -4 for this time evolution. Here is the same figure because in some case I noticed that this does not appear in some kind of, so I put together this the same picture. But in this case it's appearing quite well also, both, all the layers. Here this plot for the density corresponding to evolution of, for beta equals 0, omega 0 equals 320. The density plots are shown for solid in the middle frame. The oscillation at the resonant position, omega 1 equals 0, 0.1 omega 0. So it's 32 because the reach is 320 here with the frequency 2 omega 0. In the right frames, the non-resonant perturbator case we have. In the middle that we have resonance, and this was the beginning. And here also the parametric resonant behaviors verified for the N1 minus N2 during the time propagation. In this case, we take a very long time propagation for this Soliton system. So for example, here, when I have omega 1 equals 0, so no perturbation. In that case, this is the behavior, the natural behavior, going slowly to decreasing here now, but in a very large time now. So it's more or less constant if I take a very small fraction of time. And here, taking the frequency as 2 omega 0, omega 1 equals 32, so I can see how is the fluctuation that I have here, the resonant behavior that I have. Okay? And that is but one thing that I can see basically from here is how sensible also is, so we are expecting some resonance at 4 omega 0 there, detected by some variational approach before. At 4 omega 0 should have some resonant behavior. But you see that when I have 4, it's just slightly start changing the behavior that I have for omega equals 0. But after, if I just deviate a little bit from 4, it appears that resonant, and after going a bit more far, it goes back to the same original line. So this shows exactly how is this parametric resonant behavior. for a long time. This we conclude the analysis of region 1, shown in the previous 3 slides, with the behavior of the density. The total is this first line here, and after each component here, in a 2-dimensional plot for different time positions. So the green one is one of the components, it's just how we are exchanging the density from one component to the other component for different fraction of time. So 0, 6, 12, and you see here, just replace here to 18, and after it goes back, but the total line is the summation of both, till t equal 48. Now I go to the region 2, where I have a striped solitons solution. This region 2, where I have omega t equal omega 0 first, the atom number oscillation, take for KL equal 4 in the region 2. So large initial amplitudes correspond to large omega 0. The amplitudes decay faster for smaller values of omega 0. For the initial one, we use the difference of phase equal pi by 2 to enhance the amplitude, with beta and gamma equal 1. And here we see for different frequencies here, the Raman oscillation here, constant 1, 14, 12, 8, and 4, with KL equal 4, and no perturbation in that case, just constant. So the atom number oscillation for KL equal 8 in the region 2 for few values of omega 0 is given this slide with some enhanced only some part here from 0, 0.2, just to see better how is the behavior of this different oscillations for different omega 0 with, again, for constant no perturbation. So each line means omega 0 constant. And now it propagates that. Okay. That we can see some kind of bit here from 0.4, 0.8, and this is from 0 to 0.2, where I see these 3 lines here. 1 minute, I think the one of them looks like it's not appearing, one of only the 3 main lines here. Okay. So the region here results with omega t for region 2. So resonant interference shown for striped solitons with KL equal 8, beta equal gamma equal 1, and initial phase pi by 4. In both the cases, the resonant interference are verified for the frequency around 40 times pi. So here we have how the transfer of with omega 1 is given by the first parameter, and this is the frequency there, 127 and 26, where we observe this kind of interference phenomenon. Okay. And here is similar. There we have omega 1 equals 0. Is this that we have, so no perturbation at this point below here. And after, when I have 3 or 6, with some different frequencies, 127, the same frequency, but omega 1 is different. And omega 0, the Raman frequency is 60, and KL, spin orbit, is 8. So I go from 0 to 2.4 around this, and see this oscillation goes on. Okay. 3 components. Here is the dynamics of the density oscillation for the striped soliton. U square and V square are shown here. How the dynamically it goes to a very small fraction of time here. And I take it just to see how it appears, this oscillation. So from T0.8, I take just a small value here to see this changing of behavior for the 2 densities that I'm showing here. Okay? For U square and V square, when omega 0 and omega 1 is 40 and 2. So omega 1 is still much smaller than omega 0. So the atom number oscillation here is the upper panel. I have, in this case, again, to compare, I have omega 1 equals 0 with beta equals 0.5. Beta equals 0.5 is kept there. Omega 0 equals 10. KL equals 4, and the initial phase is pi by 8. So I have omega 1, 4, and the frequency 21.1, where it appears as resonant behaviors here. Okay? And here you can see also the densities u square v square for t equals 0, and that for t equals 8, how it more or less remains there in this position here. So in that case, I go from around 7 or 8, I think, the time in these dimensionless units that I'm using. So that's also another set of panels that I show the atom number oscillations here. For a region where usually I can see all the way like this kind of behavior, the frequency, the oscillation. But here at one point here, where this frequency goes from 35, 32, 30, and 23, decreasing here, I can see I pass it from normal 1 here, back here, but pass it to some kind of beating here, some frequencies varied here with some region of resonant interference. So for omega 32, the unperturbed case is also shown with the dashed line here. This is the dashed line in the middle. Here the case with also frequency 32, solid lines, was selected including the unperturbed case. The unperturbed case is again here, and here also the position, also at change of the N1 and N2 is difference of the population. And every time I'm showing the unperturbed case below here, and the other case with this bit. This is just extracted, I think, from previous figure also, from previous results that we have, showing how it appears this behavior. See the density plots for the case shown in the lower set of that 3 panels of previous figure, and with position x for the time interval from 1 to 3. That's for one component, the second component, where you see the more bright, more higher the densities, and here for the combining both, u square plus v square. Here are the level of the densities given at the right. Okay. Now I have just, to conclude this, I have also to show something about the high frequency modulation. How we treat that, because in those previous cases, we treat only omega 1 quite small. In that case, for rapid and strongly varying Raman oscillation, it is useful to use a time averaged Gross-Pitaevich formalism. So with omega 0 instead of omega t, with the time-dependent part of this frequency, renormalizing the spin orbit coupling and the nonlinear parameters. So by matching the averaged results with the exact full numerical one, we are also verifying numerically how fast and strong should be the time oscillation in order to validate the averaging approach. Because in some limit, we can put in doubt also the averaging, how it is working. So the averaged coupled equations are derived from this original one by using a unitary transformation. This is the unitary transformation, where Q is defined as this omega 1 is the perturbation that I have, the time dependent, with this frequency sine omega t here. It's defined here. So it's given by the requirement that the time dependent part of the Raman frequency does not appear explicitly in the coupled equation. So that's the equation that I have at the end when doing this time averaging formalism here. So you see there is omega here. I should have omega t before, time dependent. Now I have only a constant omega 0, and the part that should be dependent on omega 1 is here now. So it will give in this chi here. That is the parameter that I'm using. In that case, I have to, because of this transformation, it will transform also my parameters. No? I have to rewrite the parameters in that way. These are the 3 parameters that I have. Alpha 0, alpha plus minus, and alpha 1, which depends on gamma and also on this chi here now. And chi is defined here. So it's a frequency omega 1 divided by frequency of the oscillation. The amplitude divided by the frequency of the oscillation. So in the case of gauge symmetry with beta equal gamma equal 1 and alpha 0 equals 0 and the other equal 1, the nonlinear part of the U and V component is exactly the same as the one obtained for small u and v, such that the time average is only renormalizing the spin-orbit coupling parameter. So it means that I am only renormalizing this KL to KF, K effective. No? That will depend on this J0 to omega 1 divided by the frequency. So with omega t varying rapidly in time, KL can be turned to control the soliton in a Bose-Einstein condensation with spin-orbit coupling. It can be quite useful to transform a striped solid to regular solid and vice versa. For appropriate relation between omega 1 and the frequency omega, a given K for the region 2, for example, and region 2 is KL much larger than omega 0, can be changed to another region just by this effective approach. That I have K effective is smaller than omega 0, where we obtain regular soliton. So here is our approach that we use, in this case, a variational approach that we call multiscale method and variational approach. The wave function that are taken for the region 1 is this one here, and where this I showed before, the two regions that we are defining, and here is for region 2. In region 2, have two minima. We can take this chemical potential as this format here, where epsilon is a very small quantity, and look for solution of this form. So the corresponding bright soliton solution has this form for the region 2, where this F is a secant hyperbolic. And these are the striped solids, are linear superposition of the two modes. From this, we can get some kind of approximation solution. So the results we have in that case, for high frequency modulation, averaged coupled gross beta Evans equation, the energy and chemical potential are shown here as function of the number of particles for beta equal gamma equal 1. KL equal 8. In that case, omega 0 equals 0, and chi equal to omega 1 equals 3.7. It means that the Bessel function that I'm using for this transformation is minus 0.4, which implies that my KL equal 8 goes to an effective KF minus 3.2. So these are the energies. Here we have multiplied by 5 the chemical potential just to appear in the same scale, in the same region, the chemical potential and the energy. So here you have the real and imaginary parts of the wave function are shown for the energy minus 48.6 with N 6.86 and chemical potential minus 11. These are from the previous figures that we take, that are real and imaginary part of the two components. Here we have a real-time evolution of the soliton with omega 0 equal 120, KL equal 8. The parameters are both equal 1. For several parameters of scattering length, the beta equal gamma equal 1. For several values of omega 1 varying from 500 to 6,000. So these are obtained by averaging formalism, where K effective becomes 0, because I took just a point where the Bessel function becomes 0. So at larger time represented by T equal 4. The agreement, real time versus average result, improves as omega 1 increase, as we can see here. As I increase omega 1, the agreement becomes better. Okay? Of the exact results, no? with this approach. No? This numerical result versus the average results that we are showing here. For omega 0 equal 12, KL equal 8, omega 1 equals 200, chi I have to multiply by corresponding the parameter that is given here, 1.552, 150 with omega 0 and KL different here. For T equals 0, 2, and 8. Okay, so here I'm comparing the exact numerical results with the averaged results. As we see, that's improved for that. If I take this much larger, the agreement becomes much better. So this can be used to define the region where more applicable this kind of averaging procedure. So this is the evolution of the striped solid shown for fixed omega 0 and KL fixed, with three values of frequency omega 1 of the amplitude oscillation and frequency in the real time. So for t equals 0, the results are as with the averaged formalism, where the effective kappa equal minus 8, the spin orbit parameter. So in all the frames, I have that parameter from the Bessel function is 3.71 with given J0 equal minus 0.4. So in this case, K0 goes to 7.6. And here are the results that I can see also by increasing this value of omega 1 to 175 to 300 and improving the results. It becomes compatible with the full numerical calculation that we have. Okay, so finally I go to just some conclusions about the existence and dynamics of solids in Bose-Einstein condensation with the spin orbital and attractive two-body interaction are investigated by considering coupled atomic pseudo-spin components with time-dependent Raman frequency, which can be constant, slowly, or rapidly varying in time. So after defining the regions where we have regular and striped bright solids, we start by considering this Raman frequency varying slowly and linearly in time, so that we can study the transition between the two kinds of solid, from regular to striped one. The regions are establishing the relation between the spin orbit parameter, KL, and the constant part of the Raman frequency. Regular solitons are when omega 0 is much larger than KL square, and the other is smaller in the region 2, where I can see more maximum there. So next we study the internal Joseph oscillation between the atom numbers, which are controlled by this frequency, constant or periodic time oscillating. Now, so different parameter configurations are studied for spin orbit cap in Bose context with observed, there's some problem there. Observed parametric resonance indicate a mechanism to control the soliton parameter as well as the evolution of the soliton center of mass that we are studying. So a variational analysis that we did is valid, particularly in the case that we obtain regular bright soliton solution. The full numerical simulation have confirmed the corresponding prediction. So for high frequency, the system is described by a time-averaged Gross-Betaev formalism with a normalized nonlinear and spin orbit coupling parameters and additional modified phase-dependent nonlinearity. So by comparing the full numerical simulation with average results, we have studied the lower limits of this frequency in order to obtain stable soliton. The results are shown in several examples that we present some of them for both regions. So do the normalization of the nonlinear interaction. So new terms can emerge in the nonlinear coupling of the average system for back with tunable spin orbit cap when compared with the original non-averaged formalism. So corresponding to the phase-dependent nonlinear coupling, we have a new term, omega 0 appearing in the off-diagonal matrix terms when I transform in this procedure. This term can play an important role for non-stationary processing back and spin orbit cap, as well as in Joseph oscillation between components of solid with non-zero phase difference. So this requires some more investigation. So we expect the relevance of this study in an example, predicting some effects in possible experiments, such as lithium-7 with attractive interactions, where the spin orbit cap can be engineering as an effective two-level atoms by an uniform magnetic field with Raman laser beam. In this example, this frequency can be, for example, with 1 kilohertz, the number of atoms down 10 to the power 3, and the wavelength of the Raman laser around 804. So the Raman frequency can vary in this interval of EL, where EL is given by this, KL is the spin orbit term, is the recoil energy, and KL is 2 pi divided by lambda. So for this, we obtain omega 0 around 2 pi times 30 kilohertz. Then for the resonant case, we have the frequency 60 dimensional, corresponding to around 60 kilohertz. So the high frequency limit, omega 300, corresponds to that frequency around the 310 omega 0, 10 omega 0 should be 300 kilohertz. Okay, thank you very much for the attention.
So, thank you very much. Do you have any questions or comments? Yes.
I was just wondering, for the stripe phase, what controls the wavelength of the stripe?
You mean the
separation of the stripe maxima?
No, the stripe phase is just what controls that KL, because the spin orbit coupling also.
So it's just 2 pi over the Raman.
Yeah, because the Raman frequency because the Raman frequency is compared with KL square there. I am going to the striped phase just when crossing that barrier, because this is that gives me the difference between the region 1 and region 2, where I have solid, and that we did also change the time in a step and going from one region to other region, just to see how it's transferring them.
Any other questions or comments? Yes.
So I noticed that you were suggesting lithium-7 with a Raman laser at 804 nanometers.
Mm-hmm. This I don't know, maybe you work more experimentally with this system, could tell us if those numbers that we put there is reasonable or not.
I'm just concerned because the matrix element to both ground states is going to be the same, because the detuning of the laser beam is large compared to the fine structure splitting in lithium. So I'm not sure that you can do spin orbit coupling in that way. Maybe potassium would be a better choice. Bigger fine structure splitting.
Mm-hmm. Yeah, that we just took some number considering the lithium-7 just to find out if it was reasonable or not, the number that we took for this omega 0. But I really should have some advice of people that doing some experiment with that.
Any other questions or comments? About the dynamics of region 2, your simulation shows a clear transition from regular motion to chaos, right? The simulation of a region 2. Yes.
Interference pattern, but not really chaos, because it can go back to the... because after it is transferred, and this, if I increase or decrease that parameter, it goes back to the normal oscillation, normal oscillation. So I cannot see that this becomes a chaos, really.
Right.
Because I'm increasing those parameters, and it's returning also. Okay, I can show also some other results about that.
Any other questions or comments? Okay. Thank you very much.
Okay, thank you very much.
So after 12 minutes break, we restarted the session. Now exactly the 3 p.m. So we'd like to start the session 3:20, okay? So we'd like to start the next session. Where is the next speaker? Okay. Thank you. So we'd like to start the next session. The next speaker is Professor Peter Schmelcher. The title is Non-Equilibrium Quantum Dynamics of Ultra-Cold Bosonic and Fermionic Mixtures from Few to Many Body Systems. Okay, why not start?
Thank you very much for the introduction. And particularly many thanks to the organizers for putting together this magnificent meeting. I greatly enjoy it, and will enjoy it for the rest of the time. I think very much. I'm from Hamburg, in northern Germany. And I will tell you a little bit what my group has been doing in the past years on quantum dynamics. So dynamics going on, not stationary states, dynamics going on here calling non-equilibrium quantum dynamics of ultra-cold systems. So these are trapped quantum gases. Now there is two emphases here. One is on few to many body systems. So the approach we are choosing, I'm by education a few body physicist to some extent, at least part of me. And so I will trace the route from few to many body systems in this presentation. And then there's also some emphasis on mixtures of systems. So this can be bosonic mixtures, this can be bosonic and fermionic or fermionic mixtures. So, so the idea of this presentation is sort of to give you a clue first of all, of the underlying methodology, which actually has strong touching points with what Randy Hulet has been telling about in his theory applications of out of mean field systems, correlated systems, and the second one is to address these few to many body systems crossover. Now this is the place back in Hamburg. This is the Center for Optical Quantum Technologies. It's something like 6, 7, 8 years old. And it's a hybrid between theory and experiment. And so the ground floor is all the experimentalists there's lots of ultra-cold Bose-Einstein condensate experiments, but in particular also optical lattice experiments. And we have a small theory workshop and guest program, so you're more than welcome to visit us. This is the theory group, which you also see on this transparency, which is my group being on the first floor. So now this work, actually these works, so this is a whole series of works over the past years, which I can pinpoint only to a few of them, is based on, now this is pinpointing towards the statement of Chris, that these acronyms would be too short. Now, for this reason, we have put 2 more labels there. So this is the ML-MCDDHB. This is the multi-layer, multi-configuration, time-dependent hard for bosons. I think I'm going to explain a little bit what this is. In 2013, 14, or 12, 13, we have been developing this as a further step based on the existing MCDDHB. And then, since then, there's a series of applications. And of course, all of that would be impossible if there wouldn't be a proper funding, which is on the one hand side, the Excellence Cluster, which we have in Hamburg, the Center for Ultra-Fast Imaging, and which has been very recently renewed, or not officially renewed, but a new cluster came up in the Excellence Initiative. And then there's the SFB 925, which is a collaborative research center, which we're heavily relying on. Now, this is the contents of my talk. I'm not sure I'm going to address all these things over here, so I might take a selection of them. And so I will give you a brief introduction and motivation. So why are we interested in these correlated systems? Since I have a little bit of time, I will go into the methodology. So you get a bit of a feeling, what is the methodology about on the different levels? How do you describe these correlated systems? And why is it possible nowadays in an ab initio sense to describe systems going from, say, a few particles, 2, 3, 4, 5, to up even 100 of particles, yeah? Then I will start with a few body case tunneling mechanisms a little bit. I will strongly drive out the few body systems out of equilibrium with quenches in optical lattices. Then this is few body, something like 3 to 5, 7 particles. This goes into hundreds particles already. So we will look into metawave solitons and beyond mean field effects in metawave solitons, black and gray ones. Then there will couple collisionally 2 systems, the one being a large system, the other one being a small system, or even a single atom coupling. I'm not sure I will make it to this point, but then I will certainly try to cover these points where we make the situation even more complicated because we have a binary mixtures. The one species are ions and the other species are neutrals. So that means the neutrals are contact interacting S-wave and the ions have a polarization potential interaction with these neutrals. So that's even for any method rather demanding. And we have done there stationary, but also out of equilibrium dynamics. And then I'm not sure that there's some theory which we have recently developed for an entanglement-based induced interactions in binary mixtures, and some concluding remarks. So introduction, there has already been several talks on ultra-cold systems. I don't need to make a big reference point here, just mentioning there's a huge possibility to design traps That could be orbital lattices, there could be harmonic oscillator boxes or whatever, box-type potentials. There's atom chips. There's in particular also the possibility to control with Feshbach resonances the interaction strength, which is a great tool because usually in condensed matter type systems, for example, you do not have this opportunity. Actually, you can control these interactions through magnetic Feshbach resonances, but it's also possible optically or confinement induced, which is, of course, after all, also done with fields. So now, in more recent years, things have moved to some extent also into mimicking condensed matter type of systems, with the aim maybe at some point to contribute to the understanding of strongly correlated many-body physics, like novel quantum phases, disorder, we have heard about disorder-induced physics already, or maybe at the very end even to understand some mechanisms in high TC superconductors, maybe novel mechanisms, who knows. Then there is, this is the few-body side, we have also heard about BEC-type physics, where you have nonlinear waves, like for example vortices or solitons, and these are systems which are primarily alive on the mean field level, and then the question you can raise, of course, is, well, my system is interacting, of course, there are to some extent beyond mean field effects, what do they lead to? And then on the other hand side, with this many-body physics, there's the few-body regime. Well, some of the points which are belonging to the few-body regime might be things like atomtronics, although nowadays atomtronics is done also with BECs. You could ask yourself, how can I prepare a switch or a diode like these quantum electronic or electronics-wise motivated systems and setups? How can I maybe approach this with neutral atoms? Then transport tunneling, I will look into that, and of course quantum information processing is still a motivation type thing for cold atom. So in principle, the Hamiltonian we do have is kinetic energies, the trap, and the interaction. Now, if it is ultra-cold atoms, S-wave scattering is dominant, and then you might model your system with contact interaction. Then you have time-dependent Schrödinger equation. Then the easiest stuff you could do is, of course, you could write your wave function as a product of all particles, all atoms, in their center of mass, we consider them as point particles, in their center of mass being in the same orbital. This is the mean field equation, which mean field ansatz, which leads finally to a Gross-Beyeler type equation, being the time-dependent or being the stationary one. This is certainly an approximation, yeah, and frequently used approximation, but we are mostly interested to go beyond this. So if you go beyond this, then by definition, correlations are ubiquitous. Yeah? Going beyond the single configuration of the many-body state is a correlated state. And so you have a superposition of configurations. At least you can go that way. If you're a wave function-based person, I'm to some extent of that type. So then you would say, okay, let's make a superposition of these many-body states, and let's try to describe the correlations by making a multi-configurational ansatz. And then, okay, you're gonna have to solve this. This is 5, 10, 100, or whatever particles. You can imagine this is complicated, yeah? So, but what are you interested in? Well, you're interested in the dynamics of correlations, yeah? So, means let's prepare a certain correlated initial state and propagate it. Or let's see how correlations spread with time. Is there a way to control them? Is there a way to control a complex situation still to have desired behavior? Can you have a time-dependent management or control of correlations? And the even worse question, or even more interesting question is there anything universal in correlation dynamics, which is, no, okay, you can try to do that. So now, if you ask for a methodology, of course, there is several methods out there who can treat correlated systems, among them time-dependent DMRG or matrix product states, which are not wave function-based. But if you go for wave function-based, what you get into this system is you get quite a bit of flexibility, I would say. Yeah? You might not be capable of going to very large systems, but you're going to be very flexible. So first of all, if you do it ab initio based, and that's what we're going to be doing, you take into account of all correlations. Let's assume you get convergence. You can do it. Then including time, when you solve a time-dependent Hamiltonian, that's very natural. So any time-dependent change of the potential, of the external potential, or even the interaction is very naturally to be taken into account. What you also would like to have is at least go to a regime where interactions are substantial, are maybe dominant. Few to many body, you start with few if you go with the wave function ansatz. And then also, of course, and this is a specialty of our situation back in Hamburg of my group, mixed systems, different species, because this kind of pattern formation or this kind of formation of complex states, phase separation, quenches across phases, and this type of things, they can appear only if you have different species or in mixed dimensionality. And after all, you have this big wish list. Your method should be also to some extent efficient and fast. Now, our multi-configuration time-dependent hardware for bosons, the MLMCDHB, is one step in this direction. As it showed up over the past years, we have been pushing the frontiers of applicability of the method quite a bit, and we were very happy with that. And so when I try to give you a clue on what I mean by that. So let me, before I go into the applications, give you a bit of the spirit what the method is. I apologize upfront. These are a few pages with formulas. I hope I don't bore you too much, but I think it's good if you are capable of pinpointing to equations at some point at least, such that you know what's roughly in there. Yeah? Now, where does it come from? First of all, you want to solve numerically exact. That means don't throw away anything from scratch. You want to numerically exact solve the time-dependent Schrödinger equation for a class of interacting systems. Historically, actually, the MCDDH came out from multi-mode wave packet dynamics of molecules. So that means heavy particle dynamics, and that means that these modes are distinguishable. Yeah? So MCDDH is for distinguishable particles. Yeah? So that went back to Lawrence Zitterbaum and Hans-Dieter Meyer at theoretical chemistry at the University of Heidelberg, and has become, since then, which is 29 years now, one of the most standard tools in ab initio quantum molecular dynamics. Now, over the years, there is this ML, you know, you remember this is what is up here. The ML, the multi-layer, came already in 2003 by people Hao Bin Wang and Oriol Vendrell, and it came in a way. What does multi-layer mean? Well, in essence, it means that you repeat the whole MCDDH strategy, which I'm going to show you in a sec, on different levels of the computational scheme. So you divide your system into those different subsets of degrees of freedom, and to those subsets of degrees of freedom, you apply this multi-configurational approach. And then, after all, everything is done, you couple them together and do configurations of configurations. Then MCDDHF came in 2003. This is Armin-Skrinzi, essentially. The whole thing for indistinguishable particles for fermions. And then in 2007, Lawrence Zitterbaum with Ophir Allon and Alexei Streltsov, again, 2007. This was indistinguishable bosons, okay? And what we added on top of this is, you know, this is MCDHB, the ML again, the multi-layer structure, which allows you to become more efficient and to treat larger systems. So what is the key idea of this MCDDH? The key idea is you carry along your state space with the propagation. That means usually you would choose a basis set and would diagonalize it with a basis set, or would do you something else with the basis set. First Hartree Fock and then more, or first mean field and then more. But that you would do in a naive way, it would fix the basis. Now the main advantage of MCDDH is that you do not fix the basis, but the basis moves along time dependently with your propagation. This is indicated by this sketch. Now, this is this form. Optimally in the sense that you use the Mclaughlin variation principle from scratch, and you write your wave function. Now these are the different layers. Let me walk a little bit through this. The top layer, now this is all kind of how people call it. There's a whole kind of MCDDH language, which is not to, sometimes uses words which are occupied otherwise, but the top layer is the total wave function of the many body systems, potentially being also a mixture of different species. Yeah? or of different hyperfine states or whatever. Yeah? So, and then this is a coefficient as a function of time, and these are species functions. So if you have 100 atoms in species A, like sodium, this is the sodium wave function times product over S times the potassium wave function times. So this is a product of correlated many body configurations. Yeah. So, and these on the species layer, this is the next layer, top layer, species layer, and then you get the particle layer and the fundamental grid. On the next layer, you expand each of these terms in this product by a sum of Fock states. Now, these Fock states N are many particle configurations where the atoms are, pictorially speaking, sorted into orbitals which are propagated during time such that they are chosen optimally. So in a Fock state, you distribute the bosons among the species in a Fock state with a certain given number of orbitals. So this is a species layer function, which is one of these configurations here. So let me sort out. This gives you, so to speak, the entanglement between the species. This gives you the correlation within a species. So this is interspecies, this is intraspecies, and this is the single particle, the particle layer, the single particle function, which is also propagated in time. This is what I meant by the basis is carried along with your propagation. This is time dependence here. And finally, there's something which is indeed living on a very fundamental grid here, which is time independent. So you see there's these different layers, and also, just as a side remark, if you want to assure convergence in this whole procedure, you have to assure it on all levels of the theory, on all layers.
So there's a primitive basis?
Absolutely.
Which are time independent?
This one. Yeah. Yeah, that could be usually DVR, discrete variable resonance. It could be harmonic, sine, exponential, radial, harmonic, whatever. You can add to this if you have something which works well. So that is flexible. And actually, depending a bit on the trap, if you would have a harmonic trap, you wouldn't maybe choose a sine DVR, but a harmonic oscillator DVR. So this is it. This is the ansatz. And then you go into the Mclaughlin variation principle, and you optimize everything. You see there's a time dependence here, and a time dependence here. So what you get is a set of coupled integral differential equations, which you have dynamically truncate in Hilbert space on all layers and ensure convergence. So just to make things transparent, so if you would choose only one orbital, everything is a product here, everything is a product here, and the whole thing collapses in terms of complexity totally. Yeah. So that means Gospidevsky and all its nice and beautiful solutions like solids and vortices are the 0th order approximation to this scheme. So just a very brief look. So you propagate the A, you know the A's are time dependent, you propagate the A's, you have a standard Hamiltonian expression here, and the A is there. This is a vector times, matrix times vector, standard scheme, but you should not think it depends implicitly here with the psi with cs to the next layer, the species layer, where you have a propagation here with involves density matrices, mean reduced Hamiltonians, Fock states and their coefficients and all this stuff. Okay, then there is finally a particle layer equation of motion. Sorry, this was the top layer equation of motion, the species layer equation of motion, the particle layer equation of motion. Again, the same quantities. You have to invert these density matrix, you have these reduced Hamiltonians, and here you propagate the orbitals. Yeah? And so altogether, this is a system of coupled nonlinear integral differential equations. It's not something which you do in 300 lines, but once it works, it's something very enjoyable. So, and as Chris already asked for, the fundamental grid is time independent. That's chosen according to wise decisions. So, yeah, within the same scheme, actually, you can get also stationary states. What you do is imaginary time propagation. Then, if you want excited states, not only the ground state, what you do is you do so-called improved relaxation, where you ensure orthogonality to the ground state, and do an iterative scheme of diagonalization and of imaginary time propagation. That is what is meant by improved relaxation. Yes? Yes. Convergence you test, first of all, The number of orbitals, first of all, the grid size. Yeah, if I cover only part of the system by the grid, I don't converge. So grid size. Second is convergence in the number of single particle functions I am using. Yeah, which are described as a linear combination of these fundamental time-independent grid. Third is that you ensure convergence also in the number of configurations here. Is my system a species mean field? A species mean field would mean I have no entanglement between the two species. Could be. I could have a strong intra-atomic correlation, but very weak correlation between two species. No, this is fully feasible. If you stay, for example, in contact, let's stay contact interacting, yeah, with two species. Also. Yeah, and then you can go up with this scheme in the superfluid regime up to 100 of particles. If you say take dipolar repulsive, then this is fine. Where we run into trouble is dipolar attractive. Yeah. And generally attractive interactions are more hard. And why are they hard? The main problem comes from the fact that, that there is different length scales involved. Like for example, a bound state in an attractive interaction, I mean the attractive delta has a bound state. If I need to describe this additional length scale in my system, then I can go only to, I don't know, 10, 20 particles, then I'm done. So extra length scales coming in are a killer. A killer, I mean, limiting us. Yeah? But otherwise, we can go in the superfluid regime very well to 100 particles, also mixtures 50-50 particles, 150, something like that. This is the typical numbers we can go to. Yeah?
When you say contact interactions, that's only for one dimension.
This statement, which I'm doing now, is for one dimension, one spatial dimension. If you go to higher dimensions, there is several issues. First issue, the pure contact as it stands, delta, should not be used. This is an early work also of Brett. It doesn't converge. There's no scattering. Yeah? So what you should use is a finite range potential in this case. Yeah? What we use in these cases are, for example, Gaussians. Gaussians allow at least to some degree a manipulation of the scattering length. But again, now this brings an extra length scale. It adds here. So the particle numbers get lower if we go to crossover to 2D or 3D. Yeah? Because then all these layers to converge them costs you something. Yeah, in some sense you could view it that way. I mean, you go as far as you can go. By experience, and I'm going to show you that, if you think about, for example, when does a soliton emerge in a system, yeah? This is a question we have been posing us 10 or 15 years ago. If you treat it ab initio sense, yeah? It turns out that with 20, 30 particles, you already perfectly see a soliton in a bosonic case, yeah? With all the properties and so forth. Sometimes you need a scaling, but generally that's what it is. And with 100 particles, you beautifully see all the healing length, all the things, the phase changes and so forth. Yeah? If so to speak, you're in the very weak interacting limit, okay? Because otherwise you get beyond mean field effects. Okay, so this is a little bit what I wanted to give you an idea of the methodology. Now, let me start out with a few body case. So let me start out with, you have a few well system, a double well, a triple well or more, and you're interested in tunneling. You're particularly interested in effects of interaction on tunneling, yeah? So you want to have a bottom-up understanding of tunneling processes in optical lattices, and maybe you are aiming at controlling the transport a little bit through conditional occupation, through selective interaction, tuning, and so forth, in order to create novel tunneling processes, yeah? So there's one thing which is, meanwhile, pretty old. You see, this is going back to between 2005 and 2010. And this is just one slide on this. This is if you have, for example, two atoms, yeah, only in a double well, and they are interacting. Now, it turns out that you get something which is also the mean field analog of self-trapping, which is the localization if you increase the interaction strength. Without interaction, this would be Rabi oscillation, as you all know. If you would turn on the interaction, the atoms get a delayed tunneling, so they stay for a long time in that one well. And then, if you go even further at intermediate interactions, what happens is that the usual zero interaction Rabi oscillations turn into pair oscillations. Now, this is the pair probability, this is time, so this is what you have if there's no interaction, and this is what you get if you have comparatively strong interaction. So the pair probability stays close to 1. And you can even tune that further, such that what you have is two atoms loaded into one of the wells, and they tunnel as a pair. And this is not quite intuitive, because this is repulsively interacting bosons. This is positive scattering length. Yeah? So you have pair tunneling, which has been also detected in optical lattices and called their second-order tunneling processes. So, and if you enhance the interaction even further, you get the blue curve, and you get something like fragmented pair tunneling. So this is something very well known. Let's go one step further and take a few particles more. Yeah? Let's go a triple well. Well, triple well might be a nice counterpart of a source gate drain junction, like a transistor type thing, and you ask what is the strong correlation effects? Can I use them beyond single band approximation? So it would be beyond Bose-Hubbard model. Can I use them in order to get nice tunneling processes? Yeah, involving, in the language of beyond Bose-Hubbard, also interband tunneling. Yeah, and I'm going to show you a few examples of this. Now, the simulations were done with the MLMCT-DHB, but the analysis was done by projecting onto number states in the optical lattice. What I show you here is the triple well and its individual states. Now, what is shown here is the on-site energy as a function of the interaction strength. So what I'm going to be doing in order to trigger the processes is make a change of the interaction strength. Yeah, which we can do with Feshbach resonances, for example, as I mentioned previously. So the on-site interaction, the on-site energy, well, you can put into the triple well in each one of the wells a boson, then they are essentially not interacting. That means that you have a single mode, and this is this one, not sensitive to G. If you put two particles in one well and another particle in another well, that is, you're gonna get, with increasing G interaction strengths, a bridging between the two bands, and so your energy raises and saturates for infinitely large G. If you take a triple mode, meaning loading 3 particles on one side, you're more sensitive even to the interaction of G, and you go up to the second excited band with increasing G and saturate over there. Now, what you see in this diagram is that there is points of crossings of pair modes, triple modes, for example, yeah? And this is the points where the interesting dynamics happens, where you can steer to and look out for the dynamics. So I give you a few sketches. So we load 3 of the bosons into one well, and we switch the interaction strength, and then we go from one. What we see is that one atom tunnels to an excited band state on the right-hand side, and another state from the middle well to the central well. So what this system does is it emits bosons. Yeah. So here you have that state, 3 particles, one boson going here, and then going there and going back. So you have single particle emission of this state, and this happens. If you go back here, if you tune to this state, to this crossing here, then this happens. If you don't tune to this point, nothing happens. Essentially, your state is self-trapped and stays there. There is very much delayed processes. And you see that also here, the density, originally this is the density, and then the time evolution shows you go to a nodal state in the middle well, and a nodal state in the second well, and that's what it is. And here's the population. If you're not at that resonance position, you're going to have stationary populations. If you tune to that avoided crossing, you're going to have decrease or oscillating population in that leftmost well and oscillating populations in the middle and right well, which is due to that process going backward and going forward. There's other possibilities. You start with 3 atoms on the center well, and you do a different quench. And what happens is that one of the atoms tunnels into a superposition state left-right. Yeah? So this is one going left, going right. So this is what this means. 0, 3, 0 goes into 1, 2, 3, and into 0, 2, 1. Okay? So here in the density, this means you have a decrease in the center probability density, and you have some population. Actually now, with 2 nodes here, you can hardly see that, so you go to the second excited band state, left and right. And now, if you tune to another avoided crossing, and this is the last one I'm going to show you, is that out of the 3 atoms, one can tunnel to the left and one can tunnel to the right. Which is different from what I showed you previously, where one and the same atom was tunneling to a superposition state. And here, it's tunneling left, and it's tunneling 1 atom left and 1 atom right. Yeah? Okay, so this was a very small system. Yeah? You can make it larger by more wells and extend it. But instead of doing that, let me move on to a strongly out of equilibrium-driven system, still a comparatively small system. Yeah? So what I'm interested in, I make a certain interaction quench from the weak superfluid to the mod insulator state, and I'm interested in the phenomenology or in terms of what modes of motion do appear. This could be on-site intra-well motion. This could be inter-well motion. Intra-well would mean, okay, something like a dipole moment or something like any other on-site interaction could induce, or you could go like breathing, or you could go to inter-site interval coupling, where you can induce above barrier motion or tunneling through the barrier. Both of them are possible depending on how strong your quench is. Now, how does that look like typically? This is a small picture on this. SF stands for single frequency, MF for multi-frequency. What you see here is the density fluctuations. Okay, so there's a mean density over time, and these are the fluctuations around this mean density. So what you see is, look at the color bar, this is yellow is high density, blue is lower density around the mean. Here's what you see is globally blue, yellow. So there's an overall breathing over the multi-well system taking place. Apart from that mode, you see that motion is pretty complex here. What you also see is that on a single well, like here, that there's breathing. You see red, yellow outer parts, inner part red, yellow outer parts. This is a breathing on-site motion. Yeah. You see also that there is kind of a barrier over barrier transport. Like you have the density that comes from one, this is first, second, third side, over the barrier to the one side and kicks the cloud over there. The kicking you see here, it induces a dipole-like motion, which is actually over barrier transport, so it's more like a Gretel type kicked motion. Yeah? So all of that is in there, local, intra-well, interval, density waves, tunneling, cradles, breathing. It's just strongly driven out of equilibrium. And so now you can analyze the spectrum. You can, for example, look into the fidelity. If you look into the fidelity, Fourier transformed, you get the frequencies, you get the modes of the motion. For special quantities, other observables might be interesting, but generally you get this frequency spectrum, yeah? And you get all the tunneling branches, which you can analyze, you can understand the bunching and so forth, but let me address finally one specific case. So what you see here is the Fourier transform of the so-called intra-well asymmetry. So the left, you take one well and there's a left-right asymmetry. Like for example, the dipole mode, there's a left-right asymmetry here. So, and you look into the dynamics of the integrated density of the left and the right, the difference of the left and the right. And if you do that, then when you look into the spectrum, and this is only a small portion of it, in a certain frequency window, you see, for example, this avoided crossing. And you see also that it is yellow over here, which means it is resonantly enhanced. Now, if you look into the dynamics of these branches, this is actually a tunneling mode which has an avoided crossing with the so-called cradle mode. Remember, the cradle mode was over barrier transport kicking the system. Yeah? So what you can do now, this is the interaction strength. What you can do now is you go into this this complex situation over here with many modes. You can steer to a certain interaction strength, and you will resonantly enhance just these two, the coupling of these two modes, which then leads to a characteristic beating behavior in the corresponding quantities. Yeah? So out of this complex situation, by tuning appropriately to the avoided crossings, again here also, in modes, in frequency space, you can get a degree of controllability of the system. Now these were comparatively small systems, yeah, something with 5 to 10 particles, yeah. Now let's go to beyond near field correlation effects. In a typical nonlinear regime, in a regime where you have possibility for very weak interactions to see nonlinear waves like matter wave solitons, black ones which are zero velocity, or gray ones which move. And let's look into that one. Now, n weakly interacting bosons, we put them into a trap, we put them into a box for our case. We simulate the complete preparation procedure, usually in order to create a dark soliton, which is usually phase imprinting, so you print a phase on the left, on the right, because the soliton has a phase jump or phase change across its density notch. This is repulsive interactions. So, so you do a robust phase and density engineering. There's lots known about this. There's many papers about solitons around. And once you exploit all of that, which is to the good, because you don't want to create too many sound waves in your system, so it helps you to prepare a clean soliton, then you get this. This is the one-body density in space as a function of time. Now, the inset is mean field, and the original figure, the large figure, is what you get from the many-body calculations. This is, for example, for 100 particles. In the box, the Lieb-Lineker parameter would be here 0.04 for those who have heard about this. So what you see is with increasing time, it broadens. This is the notch of the soliton, yeah? So this is a zero density essentially here. This is a black soliton, and it broadens, and which is not present in the mean field case. And if you have a gray soliton, this also broadens, but much less, and with increasing time. Now, just going back, this is, for example, a calculation with 4 optimized orbitals, yeah? And of course, you ensure you go to 6 orbitals, ensure that everything is converged. Particularly, as you shall see in a minute, what you have to ensure is not only the density to be converged, but also the two-body correlations. Because what happens here is a correlation effect. Yeah? So what you see here first is the contrast. Now the contrast is the difference of the densities at 0, where the original soliton was, and the minimum later on. And you see how this contrast changes. In the case of a black soliton, which is kind of standing soliton, the notch fills up very rapidly, but if you move over to more gray solitons, they fill up to a much lesser extent over the same time period. And this is the quantum depletion. So you see for the black soliton, yeah, it is beta equal to 0 here, not moving, yeah. Beta is the U over S, that's the velocity of the soliton divided by the speed of sound. Then you see that the depletion goes quite rapidly. And if you're gray, it goes less rapidly. Now, what is the physical process which is taking place? Because we see that the notch is, on the one hand side, broadening, but it's also filling up. Yeah? So the contrast is getting smaller. So it means that the notch of the soliton is filling up. So what you see here is the two natural orbitals. So this is the orbitals that diagonalize the single particle density matrix. If there is only one orbital participating, this is a mean field process. If there's several orbitals participating, this is a beyond mean field, a correlation process. So what is shown here is the dominant and the second dominant natural orbitals. Let's look at the first one. Now, this is, of course, having already signature from correlations, so it broadens, that's what you see, here for the black case, here for the moving case, and what you see that the second orbital is filling up the notch. It's gaining density over time. Yeah? And also in the gray soliton, it's gaining density. So the two orbitals naturally have an interpretation which tells you the one is maybe or keeping the structure of the original soliton except from widening, and the other one is filling it up. And these are the phase profiles correspondingly. So now let's look into what happens indeed in the correlations, because so far this is single particles still in the sense of the analysis. It's the diagonalization of the single particle density matrix. So if you look into the two particle correlation function, what you see is you start here, you see this is very small numbers, so essentially this is all diagonal. If you look into that one, the numbers are very different here compared to here. You see that there is a strong amplitude on the diagonal. So what you have is, for this black soliton row, you have a bunching of particles. What happens, there's a two-body process in the notch of the soliton that leads to scattering, that leads to filling up of the notch. And it widens and broadens over time. And so you have a bunching on the diagonal and an anti-bunching of the off-diagonal. And this is the same thing for the gray soliton, where you see that there's a correlation spreading and direction preferred. So in the back cone of the soliton motion, there is this bunching. In the forward cone, there is an anti-bunching here. But this is truly the dynamical process which leads to these kind of correlation-induced beyond mean field dynamics for these systems. Now, actually, how much time is left? 5 minutes. That's really tough. So let me jump over. This is a collisional coupling of a system. Let me just give you 1 minute on what we have very recently been doing, and then maybe 3 minutes on what is the atom-ion hybrid system, because this is a very intriguing system. So maybe I should spend a few words on that one. So more recent projects, you see this is, all the stuff before was something up to 2014, 15. And then with increasing years, we got more and more control in applying MLMCDDHB. And the result was that we went into more complex systems, like correlation effects across quantum phases. Yeah, like systems there, you have two species, dark bright solid dynamics beyond mean field, or even more recently, the main focus is on polaron and impurity physics, repulsive polarons formation, spectroscopy of those systems. You can simulate the whole spectroscopy process. Then impurity dynamics, particularly how a trap can induce negative mobilities, how you can achieve orthogonality catastrophe, Bose polarons. So this is the more recent stuff. But I will use my few leftover minutes in order to talk a little bit about a system which is very hard, both experimentally and particularly also theoretically. This is atom-ion hybrid systems. Of course, from an experimental point of view, I think I do not need to go into details. It's simply complicated because you have to trap ions and atoms, which are completely different technologies. And cooling ions to the ground state is still a challenge. But there is rich prospects ranging from chemical reactions, charge transport, spin-dependent interactions, to maybe emulate really vibrations, because in usual optical lattices, you have a fixed potential. But if you would have an atom-ion hybrid systems, you could mimic also the phonons of a bulk. So you get an extra length scale, which is, as I indicated already, painful for MLMCDDHB because you have that extra polarization interaction, the extra length scale R star due to the polarization. Now, you can go through this. It took us 1 year to do the right modeling, link the quantum defect to the potential and all this stuff, and put that in and implement it into the multi-layer but the outcome was quite interesting. Yeah? Now, this is an atom-ion hybrid system. So that means, actually, since I have that attractive interaction, 1 over r to the 4, I can also not only have that soup of neutral atoms around there, which is an ultra-cold gas, but it can also bind atoms into the neutral ground state, into the ions, into the ion. So that would mean I could have a molecule, a mesoscopic molecular molecule, which was actually as a polarization cloud early predicted by Robin Coté. Now this is here exact quantum simulations. But then I could have also something like some atoms live in the gas and others are in the bound state. Now in principle, if these atoms are not interacting, they could condense even into that weakly bound state. Yeah? But if they are interacting, only a finite number of them can go into that bound state. So what can happen is you can have formation of an ionic molecule. This becomes a massive quantum object because you put more and more into these states. Yeah? Then you will get a phase diagram. I will show that to you in a minute, yeah, of the compound system. You can have a shell structure formation because there's not just one state. There's an even parity state and an odd parity state. And you can probe the response of this mesoscopic system to external changes of fields, for example. So you can look at the dynamical response. You can have dissociation processes. What you get is self-localization. The object gets more massive, yeah? And you can have that molecule, but you can have the molecule also in a bath, which is, say, it binds a certain number of atoms, but then there's still a surrounding cloud of neutral atoms. So there's a rich physics in there, which separates two regimes. The one is the negative chemical potential, the positive chemical potential. The one is this mesoscopic molecular ion. The other one is some atom or a cloud of atoms still surrounding it, which is then for positive, as I said, chemical potential. Yeah? And you can understand in detail how this comes about and what the critical binding number of atoms is depending on the interaction strength of the neutral atoms. Yeah? You can choose different approaches and you understand very well what the correlation effects are. Actually, this is mean field. So this is the energy as a function of the particle numbers. This is mean field. This is Gross, early approach by Gross, which goes to a different reference frame, and through this different reference frame includes correlations. And then the true behavior, which is the fully correlated from the MLM-CTHB. And you see the difference is you're lowering in energy, but you're shifting also the critical particle number up to which you can bind particles. Yeah? And then you can understand this structure. Yeah? So what you see here is that the ion density more and more localizes with increasing particle numbers, and it forms a subcloud of the overall cloud. And in the same time, the ion neutral atom density becomes two-winged in the density and develops also an outer wing, which is this kind of neutral soup around the mesoscopic molecular ion. That this is indeed a correlation effect, you can also probe by looking into the atom-ion correlation function. And what you see here, that there's this kind of strong correlation peak at a finite distance, which is these wings around the ion where the bosonic atoms are condensed into here. And then this is just a picture which distinguishes between even and odd parity states of these condensation of the atoms. Yeah. This is explaining how the self-localization goes, actually. This is the variance of the ionic and the atomic cloud. And if you look into mean field, that is down here. Yeah? So it's far off from what truly happens. But you still, what you get is zero interaction here, then it is monotonically getting smaller, yeah? And if the true case, the interacting case, really goes up. This is actually the point of the critical particle number you can bind, and then the energy goes up to positive chemical potential, yeah? So this is something like a molecule under pressure, or a cluster which is formed under pressure. Finally, how would you probe that? Of course, you can apply a field. This is one way to do, and theoretically, how you get the response of the system. you can, of course, apply an external field and observe the quasi-particle. This is a kind of a quasi-particle. It's an effective single particle picture, and see what is the effective mass. This is the graph over here, or what is the effective frequency. It's fields in this overall harmonic potential, yeah? And both of them you can understand pretty well. Here it is not done dynamically. You don't switch something in the MLMCD-DHB simulation, but you get the effective mass from a force commutator, yeah? So what you see here is with particle number, that scales linearly, then sublinearly, and then it goes up, yeah? And then from that point on, essentially, this is not a quasi-particle picture you should apply to the system to describe the system. But up to that point, and say up to that point, this quasi-particle picture is valid and gives you the correct response. Meanwhile, we have done also dynamical simulations which agree with this force commutator approach. Yeah, with that, I would like to conclude. I think my time is more or less over, and I'm going to switch to more towards the end. I hope I could show you that this, the tool, the MLMNCD-DHB, is a versatile tool. There's many different physical situations where you can follow nicely the dynamics. Even it has quite substantial correlations in it. The particle numbers you can treat depends on the system, ranging up to hundreds of particles. And as I said, depending on systems, you can strongly drive out of equilibrium, but if you do, the more you drive out of equilibrium, the more it is difficult to describe. But there is many open routes. In particular, the one we are pursuing is the mixture stuff, and as I said more recently, the polaronic and also the impurity physics. Yeah. Thank you very much, and I'm ready for questions.
Thank you very much. So, yes.
In the dark soliton case, you went to m equals 4.
Yes.
What do you lose if you only take 2 natural orbitals? What is the effect? Do you have intuition on that?
Yes.
On the preceding.
Yes. To converge these two bodies. Yeah. Sorry for that. To get this converged here, 2 is not enough.
2 is not enough?
No.
You see it?
Yes.
It's gross?
Yes.
What is the effect? What changes?
You see, that one would be the filling of the notch. These are 2 orbitals. Yeah? But it would smear out what we have here, yeah? If I would, so this is the 2 dominant orbitals. That would give you, if you do a 2-orbital simulation, already the filling up of the notch, but the correlation behavior with 2 orbitals would not be fine. It would smear out. Instead, it is very localized to the notch. Yeah.
Yes.
I'm trying to visualize how you would form these hybrid systems, because you put an ion into a gas of neutrals, you get a sequence of recombination events triggered. You first have 3-body recombination, which makes a molecular dimer, charged molecular dimer. Then that is still attracting more. You get more 3-body recombinations. It's releasing all sorts of energy into the cloud. I don't see how you would get into this state that you're talking about.
Yeah, well, this is all elastic, what we have here. I completely agree with you. There's no chemical reactions in here, yeah? Okay? So it would assume that you would have the capability of suppressing all these chemical reactions, yeah? Like you do it for, I don't know.
But you could run your simulation, couldn't you, just with a different initial condition and actually see this chain of recombination processes happening?
Oh, no, this is not in my Hamiltonian. This is not in my Hamiltonian. Yeah? I mean, not at some point back.
Free bosons and a free ion is not in your Hamiltonian?
No, but what you are referring to would be, maybe I misunderstood you, but I thought you mean really forming bound states out of collisions, for example.
Right.
An ion, yeah.
But you have bound states.
Yeah, I have bound states, but only the most weakly bound states. I wouldn't have more tightly bound states.
Well, of course, but I
Yes.
mean, the three-body recombination at low, ultra-cold temperatures predominantly makes these weakly
Yes,
bound diamonds.
three-body interactions are not in here.
But you don't even need three-body. This all happens with two-body forces.
Okay. Now so what is your final state which you're addressing?
Well, I was thinking of a time-dependent process.
Yes.
Where you make molecular ions, polyatomic ions, first diatomic, then polyatomic ions, starting from a free gas of atoms and ions.
So what is formed is indeed a bound state of an ion and neutrals. In this last bound state, in the 1 over R to the 4 potential. Is this that ones you're having in mind?
I guess you would be forming those, yeah, but also at the same time releasing a bunch of energy as
Absolutely. Yeah. Okay, now I
through
got
the
your point.
recombination
Now,
dynamics.
indeed, if you do the simulation, most probably you're referring to that one. You, for example, prepare your system in a state where you're not in the bound state, but you prepare, and then you let it run. What happens is dynamically you populate those states and you scatter out of those states, and you can monitor this. This we have done, yeah. But what I've been showing you here was the quantum phases.
Yeah, that's what I thought.
There was no dynamics.
Like the ground state.
Yes, absolutely. So
I did have one other really short question. Trying to decide, are you having a creative spelling of the word cradle when you call it cradle, or is cradle a whole different concept that I've never heard of?
Well, yeah, you have over-barrier transport, yeah? And you kick the density on the other side.
No, I'm just asking an English question.
An English question.
Is it cradle or cradle? Because there is an English word cradle, and cradle I've never seen.
I see. So you're the expert.
Oh, okay. So you do mean cradle.
Yeah,
I
cradle.
just thought maybe it was something I
Okay,
hadn't
okay.
heard of.
Fine with that. No problem. My English is not perfect.
Any other questions or comments? Yes.
So actually I have a question concerning one of the transparencies you flashed very quickly through.
Yes.
Is referring to a paper you wrote on orthogonal catastrophe for bosons. And I'm more familiar with orthogonality catastrophe for fermions, and there they play an important role for excitons, for transport. And I have then two questions. The first one is, what are the physical phenomena involved here in bosons? And the second question is, since you speak about multi-configurations and stuff, is this a generalization to multi-configurationally or just the simple orthogonality catastrophe where it takes Slater or here permanent states and change them?
Actually, it is not a new phenomenon, but it's the standard orthogonality catastrophe. Yeah. And now I don't. What was your first question again?
So what are the physical phenomena here for bosons that are important that you address with that?
Well, first of all, the formation in the quench dynamics, yeah, of the Bose-Polaron. Yeah. Yeah. So you start actually similar to what you wanted to. You don't start with a Bose-Polaron. You start with something, a situation which doesn't have it, and then you suddenly trigger the dynamics, and you dynamically observe how it forms. Yeah. Okay. So you go to the Fourier spectrum again. You observe the quasi-particle peaks, and you see that appearing. Yeah.
Any other questions or comments? Yes?
Actually, I was also interested in this orthogonality catastrophe. So what is catastrophic?
Well, actually, what is catastrophic? Well, the orthogonality which that emerges in the course of the dynamics. Yeah, that's.
No, but does this mean there's a collapse? Why is this called a catastrophe?
Now it's going back to your nomenclature type thing, yeah. Maybe we can discuss this privately. Yeah, you shouldn't take it. Yeah. No. Yeah. Yeah. Yeah, there is no catastrophe in your common sense. Yeah, sure, in that sense. There's no resonant response or anything like that. It's just.
Okay, any other questions or comments? Okay, then we'd like to thank Peter. Thank you very much.
Request something. Please, for those who haven't done so yet, I would like to request that you send me a copy of your boarding passes for your trip coming to Sao Paulo. I got from 2 people, but I need from the other 4. You send me one. Yeah. The others didn't send me that. Okay, thank you.
Coming.
Okay.
So the last speaker is Professor Arnold Gamal. The title is Mixtures of Dipole Condensates and Rotation and Lattices. Why not start?
Okay, thanks for the opportunity. Thanks to the organizer, Professor Hussein, Professor Vanderlei, to organize this nice workshop so as we can merge our knowledge. So we are talking about mixtures of dipolar condensates and the rotation, and they will show lattices formation just after that. This work was made with collaboration with a postdoc, Kumar, that will appear, with Lauro Tomio, that is in the audience, and there is one part of the work made with Boris Malomed and also with Pausami, Murugan Andam. And let's go on. So first I made an introduction. I will talk generally about dipolar gases, and there are several experiments that have been done and its relevance. Then I will discuss a little about miscible and immiscible transition, how different is miscible from usually oil and water, and we'll discuss that. Then we will see, we will rotate those condensates and see vortices, lattices. And finally, we can also tune the interactions of this rotating BEC. First of all, there is contact interaction, mainly come from van der Waals interaction, and it's given by the delta potential. And also there is dipole-dipole interaction. In the beginning, contact interaction was mostly studied. Later on, people realized that the dipole interaction could be very interesting to study because of this relation to condensed matter physics, also with spins and magnetic phenomena in condensate. So this is, people see opportunity to understand condensed matter with Bose-Einstein condensate, since you can tune many things, so it's much more flexible system than general or usually condensed matter in a fixed solid or something like that system. About discussing the dipolar interaction, you can also have either magnetic dipolar interaction, that is, first experiments were done with alkalis like chromium, done with chromium, and you can also have much bigger interaction with erbium and dysprosium. Do we have light here? We have a laser here? There's a pointer? No? No? This point? No? Doesn't work on the screen. Ah, okay, no problem. So, okay. And so here is a comparison between different atoms. We have rubidium, sodium, and how the magnetic dipole interaction is changed. Ah, thanks, many thanks. So how magnetic dipole interaction is changed here as long as you go to erbium and dysprosium, and things get really more interesting and more favorable for experiment. And also there is possibility for going to heteronuclear molecules, and then in this case you are talking about electric dipole moments, and even Rydberg atoms, maybe someone will talk about this. And okay, so here in this region of rubidium and even chromium, we are in the weak dipoles, and then we can have strong dipoles. So we, in our calculations, we are mostly working with erbium and dysprosium and analyze their mixtures. So there is a lot of experimental progress in dipolar BECs. There was in the beginning stability analysis. Just after they make chromium condensate, they make stability analysis, compared how should be the stability of pancake traps against cigar-shaped traps. And as you go more cigar, it can be more unstable, showing this. So most of our calculations I will show you later will be more in the pancake, more in the stable side. Here is the collapse, the anisotropic collapse that was made with dipolar condensates. Typically, when you have just contact interaction, you have isotropic explosion, implosion and explosion. Okay. Here is showing dipolar interaction, dysprosium droplets in a waveguide, dysprosium collisions in elongated traps. So many experiments done by Innsbruck, done by Tillman-Fowle, also different groups working on dipolar. And now I heard that São Carlos also is doing something, I think dipolar, no? They're doing something dipolar. Okay. So there is also other experiments about droplets crossover studying the Lee-Huang-Yang interaction, it's quantum fluctuations, and striped states in dysprosium BC. So now dysprosium and erbium has somehow being common in those experiments. Also, there is a lot of theory have been done in dipolars. Here you can see the stability analysis made by Honen and collaborators. You can see this shape, this concave, biconcave shape, and as long as you come here, you become more biconcave. Sorry, the reverse. As you come here in the darkest one, it's more biconcave, and the black, the white one region is the unstable region. Here there is also structured cases in anisotropic traps, so it's not so simple. As you turn on dipolars, then can be very fancy formations, even ferrofluidity. So a lot of phenomena can appear in. Here's also droplets of dysprosium. Also, there has been interesting work on droplets from BEC to droplets as time evolve, and also striped states. So this is our general dipolar physics that has been done. Just an overall review about that. So we are analyzing the multi-component BEC, in fact not multi, just two components we will do. And we use two different hyperfine spin states, mainly erbium and dysprosium. The importance feature exhibit miscibility and immiscibility behaviors. And there will be this spatial overlap between the wave function in each component. So here are some experiments about miscibility in non-dipolar physics, in rubidium, sodium, rubidium, and the immiscibility in rubidium, cesium, and also here in rubidium, different states of rubidium. So our main concern is about miscibility of dipolar and non-dipolar BECs. So we studied three-dimensional of miscible and immiscible conditions for dysprosium with different isotopes, and erbium dysprosium. Of course, there are many isotopes of dysprosium, and erbium dysprosium, and we just choose some of them, the bosons, so as to make our study. And what we made, we made the calculations to see what's the aspect ratio, how the aspect ratio can change the miscibility. And also we have studied the stability of the system, how the systems can be made, and we will show non-trivial minimum biconcave shapes with density oscillation. So here is Kumar, that is, after 4 years in our group, he returned to India. Here is Muruganandam, he is India, Lauro is here. So the equations we solved, we did it in mean field. I challenge to solve this in the multi-configuration way. I don't know if you can do it any way in the multi-configuration to solve this dipolar. So from now, I just see that we can do it in the mean field approach. Maybe, I don't know, three-dimensional, to do it in multi-configuration will be extremely complicated. Anyway, we have two complete Gross-Pitaevsky equations, and we have, here's the contact interactions, and here you have the dipolar interactions. The D11 is the self-species interaction, D12 is interspecies, it's between species interaction. And we have two components, can be either erbium or dysprosium or even rubidium. And then these parameters can be rescaled for proper calculation. In fact, they are already rescaled for proper calculations. Here is the dimensionless. So all parameters in these equations are dimensionless, rescaled. And critically, this is the dipolar interaction magnitude that comes here, that somehow comes in A here, and then comes to this d, to small d's here. But everything is renormalized in dimensionless way. So here I discuss a little about the miscible and immiscible transition. In the beginning, we thought, okay, if you mix water and oil, you always have a clean separation. But when you mix gases the way we do quantum gases, there is always interpenetration of one species and in the other. There's usually not always full miscibility and neither full immiscibility. Either always there is some interpenetration. So we understand that we must use some parameter in the case that complete overlap of the wave functions should be should eta equal 1 should means miscibility, and eta equals 0, no overlap. After we saw that these guys formerly already defined the same parameter, so we understand that we are doing the right things. So this is measure how they are miscible or immiscible. So here, these diagrams is a study about the stability of the system, not exactly the first, you must know if your system, it doesn't help much to know if it's miscible or immiscible, if it's not stable. So depending on the aspect ratio, as you change the aspect ratio, you can go from stable region, as here you lambda is, as you have, you are more pancake here, you can go, if you go to more Seeger, you go to unstable. So it depends on the mixtures, it depends on the number of atoms, depending on how you change the number of atoms, so from one species to other species. It depends on the ratio. So for experimentalists to perform an experiment, first of all, they must be in a stable region, and it depends on all the parameters to be stable. So the better thing you go to pancake trap, you more safely will be stable. So here's some analysis of the miscibility of the parameters. So as I said, in this case, it's not so easy to say, oh, it's completely miscible. It's not completely miscible. And with this eta parameter, we can somehow quantify the miscibility. Maybe you can devise another parameter or other kind, but anyway, it's a reasonable parameter. So here, eta is 0.77. This is the miscibility parameter here. So here another example with now with dysprosium. Formerly it was erbium dysprosium. Here is dysprosium, and since the magnetic moments and all parameters are more similar, they mix better than erbium dysprosium. And here clearly we see they are very well miscible with eta is 0.99. And here is a diagram comparing non-dipolar condensates with erbium dysprosium mixture and dysprosium. And as you change the asymmetry parameter of the trap, and clearly it's better if you want to do experiments, it's better you go from here, you are in stability region. Otherwise, you can be, in the non-dipolar case, you can have all parameters, but in the dipolar case, you clearly can be unstable. We fixed the scattering length for all in general, for this paper, we fixed the scattering length in 50 A0 to make our analysis. So some examples of the aspect ratio, what can happen in the aspect ratio. So this can be in the cigar shape case, and this in the pancake shape. So clearly the projection of the wave functions can be completely different in those ways. So here is completely inside, and here is sideways. Well, it's 1D compared to 2D. You just shrink it, everything. Here is an analysis of the miscibility parameter for several here for different scattering lengths, and as long as you decrease the scattering length, it becomes more and more miscible. And here the analysis is made for different dipolar interactions. What I mean by erbium or dysprosium. So there are many lines here. I will not describe all of them anyway. Here, the role of the scattering length of A12 here, A12, changing A12 will change the miscibility. So in this case, we are seeing that fixing dysprosium, if you change the scattering length, it changes a lot also. So in principle, you can control the miscibility of the system with Feshbach resonance in the scattering length. You can control it, even the dipolar interaction in this case is not being changed. So you can see here it's roughly immiscible, and here it starts to be immiscible. Here there is separation of phases depending on the scattering length parameter. So now I turn to a different issue. When you rotate condensates, you rotate mixtures. Previous work by Tsubota and collaborated in audience and collaborators, they understood that when you rotate mixtures, you form lattices of vortices, but depending on how you rotate, depending on the parameter, there is an interaction parameter. When you change the interaction parameter, you can have this transition from vortex arrays to this different pattern that have, let's say like a labyrinth here and this formation. And this depends critically on the scattering length. So we did an analysis like this, but in the dipolar case to understand what's the difference, and if we have different patterns compared to this previous work in the non-dipolar case. So we changed the coefficients of the contact interactions, and we see several types of lattices, and depending also in the frequency of rotation of interspecies scattering length. And this work was collaborated also with Boris Malomed. So another time we take the same Hamiltonian, but in this time we have this rotation parameter. And as I said, we take the asymmetry parameter much bigger than what I mean more pancake trap, in a sense to avoid problems of stability, and also to make easier the calculation. Here we make the calculations in a 2D environment, so as we make an effective 2D interactions. So everything is effectively in 2D. It's the 3D, but effectively the calculations is 2D. You make a reduction to 2D, either in the contact interaction and in the dipolar interaction, and we make the calculations in the 2D way. So, after including this term, we have, we also, I showed that the calculations in the 2D need different, typically for doing in 3D, there is a standard way for doing the 3D. Because of divergence of parameter, divergence of R cube in the interaction, usually we do it by fast Fourier transform, and solving fast Fourier transform this part of the interaction. In the 2D, you have to make a different but similar Fourier transform. It's a different way to do. It's just a little different, but anyways, the trick is the same to avoid the divergence. To make our calculations, we also choose an initial basis with all the angular momentum initially in this pancake trap. All the angular momentum were, it's a summation of all angular momentum, and here we have random phases, and we make the calculation many times with different initial conditions, because the calculations can change when you propagate in imaginary time. The final result depends on your initial, because you can find some metastable states and your code gets trapped there. So to avoid that, we started with many different initial conditions. We searched randomly these initial phases so as to accommodate many possible initial conditions. And then we ran it many times until we were satisfied that that one is the lowest energy state. So these are grid points, typically grid points. We use it 500 and these works were all done in workstations, either here, partially in India too, using other computers. This trick we took from Bhutan Hoxha. In fact, he doesn't mention to use this trick, but his expansion, we foresee that we can use his expansion to do this trick. And here is a phase diagram of vortex patterns, depending on this ratio of scattering length parameters. So depending on this scattering length, you can have triangular, you can have squared. I mean, these positions of the vortices can be in triangular arrangement, squared arrangement, rectangular, or even double cores, and striped and domain walls. So this is the diagram, and depending on you change this delta parameter or this rotation parameter, the rotation relative to the trap, it will change dramatically all this phase the phase that you can see in this diagram. So here are some examples that we have run and solved. Here, delta is the ratio between the scattering length, the A12 over A11 is the ratio. And as we change this ratio, we change here from one pattern, we are changing to different patterns. And also, this line is from one condensate and one species, and the other line is the other species. This is for dysprosium mixture, and the rotation is only 0.4. And here, as we increase this interaction parameter, we see that as long as the interaction increases, then the interspecies interaction increases. There is more interpenetration, and these fancy figures similar to those found by Tsubota previously, but not in the same range. They are different anyway, because here is the dipolar, and it changes a little the patterns and the regions where it happens. So here is the patterns: square, rectangle, double core, stripe, and domain walls. As here, the frequency is 0.6, showing the different standards. Of course, in Tsubota paper, there is some theory about this, in fact, predicting where it's going. But here it's much harder with the dipolar interaction. The analysis is much more complicated, and we can only do qualitative analysis. And here is erbium-dysprosium mixture, and the phase diagram is obviously different. And here we have more delta, more squared formation, triangular formation, and the ring lattices that I will show you. So here is the erbium-dysprosium mixture. So interesting phases happen here. As long as we increase delta, one species goes to the center and the others go to the outside of the condensate, of the outside part of the condensate. And here, with different parameters, with different rotation, here we have more spread out condensate, and another time it splits. So it's general that it goes, one goes to the center and the other goes to outside. The last part is about tuning the dipoles in rotating these dipolar BCs. In fact, you can tune the dipolar interaction. It has been shown by the group of Thielman-Fau and recently also by Lev and collaborators, that once you change the magnetic field appropriately with a frequency, you can have an effective dipolar interaction, giving not only by this standard expression by dipolar interaction, but then you have an extra term depending on this angle between the dipoles and the z direction, the polarization, the z direction. And theta is the angle between the line that join the dipoles. So in principle, you can, not in principle, in fact, they tuned the interaction of the magnetic field. So we pushed, after we did some calculations, we put the question, okay, what happens if we can tune also the dipolar, not only the scattering length, but also the dipolar interaction. And once, so we choose the simplest case, that will be the pancake trap, and the theta angle will be just 90 degrees in the pancake. Once you compress to the pancake trap, you'd only have, the theta is 90 degrees, and now you are free to change this angle and to change the interaction parameter. Another time you have to in two-dimensional space, you have to make this transformation to make the pancake trap, and this in particular case. And here is our study we did in dysprosium mixture. So here, if you go across, so here we are changing either the delta parameter. Here from time to time we change the delta parameter, and in this direction we change the interaction parameter. We change this angle. I mean, we change the dipolar interaction. So as we can see, so for phi equals 0 is the standard results that we got previously. It's the same results that we got previously. Is phi equals 0. We go from this square lattices of vortices, and we change to these domain walls that we are going on. And then if you go in this direction, then different things can happen. If you see, once we tune this dipolar interaction, you can even have the separation of phases here. It's a very unpredicted, not obvious thing that could happen here. He is completely separated the phase. In fact, when you see things happening, okay, it looks natural because the phases, let's say, these domain walls become thicker and thicker, and in the limiting case, they should separate somehow. It's what exactly is happening here. So this dipole-dipole interaction tuned can separate the phases in this case, in the dysprosium mixture. Here's some interesting thing in when they separate, you can also analyze very carefully what's happening on. And if you plot the phase space, you plot the phase of the system, you see it appears some ghost vortices. And this, not exactly whole ghost, some hidden vortices. Those vortices are very low density vortices that you don't see them exactly, but to make through some Feynman calculation, there's a Feynman formula for number of vortices, and in some cases you must include these hidden vortices so as the Feynman formulas become true. We don't understand fully these hidden vortices, but we decided to show them also in this what is happening here with these vortices, the hidden vortices. Here I show the same calculations now with erbium and dysprosium. And as you see, we don't have the same kind of separation as dysprosium, but they exchange places. Here, depending on the interaction parameter, for instance, here you have in the center of the trap erbium, and then at the end once you change the scattering parameter, they become outside. And this is turning the dipole presented a richer figures of the ground states of this system that is not so easy as in the case of the contact interaction. There is a lot of richness in the states once you consider the dipolar interactions, a lot of liberty of changing parameters, in particular this exchange of depending on you change the tuning parameter, the magnetic tuning parameter, they exchange positions. Okay, in conclusion, we focus our study in the coupled erbium and dysprosium. We observed non-trivial biconcave shaped structures that I didn't show all of them, with local minimum states of both components and couplet system and the emergence of density oscillations. The role of aspect ratio and interspecies contact interaction for miscibility and immiscibility phase transition was studied for different configurations and dipolar system. Vortex lattice structure is studied by varying the coefficients of contact interactions and the rotation parameter. And we present phase diagrams for several types of lattices, in the parameter plate of the rotation frequency and the ratio between inter and intraspecies scattering length. The mass imbalance sensibility is verified, and since you have dysprosium 164 and 164, there is some mass imbalance sensibility to these calculations. Small difference of masses changes everything. There are vortex structures found to be diverse for dysprosium, and erbium, changed pattern. Also anisotropic effects in dipolar interaction related to spatial separation and miscibility are discussed. And complete spatial separation is verified in the attractive dipolar-dipolar interaction when inter and interspecies contact interaction is larger than 1, being angular for symmetry mixtures 164, 162, and the radial for asymmetric erbium, dysprosium, and dysprosium rubidium. Finally, there are recent experiments in 2018 by a group of Innsbruck with mixtures of erbium dysprosium. They condensed erbium dysprosium, and this is the latest paper they are doing in dipolar quantum gases. So I hope that they can do or perform some of these figures that we went through. Thank you.
Thank you very much.
I have a question or comment. The two coupled Gross-Dostoevsky equations basically represents an effective polarization interaction in the atom-atom case. I mean, it's complicated to add, so you split this into two equations. I mean, in Feshbach's original work in nuclear physics, you always find these, coupling between one particular state with another state, and you eliminate the other state, and you have an effective equation for the first state. Now, psi 2, which, of course, to split it in two equations is much easier to handle. Now, psi 2 could be anything. I mean, in principle, in your case, it has to do with the dipole interaction. But psi 2 could be molecules. Certainly, I mean, with a change in the atom-atom interaction through Feshbach resonances, you could form molecules or quasi-molecules, and these molecules would represent a depletion of the Bose-Einstein atomic gas. But, I mean, to handle that dynamically, you will have two equations, one for the atoms, one for the molecules, and the coupling between the two would be something like a Josephson interaction. So it couples from atom gas to molecular gas and vice versa. So it have basically oscillation in the density. The atom density goes down and up, and the molecular density starts from zero and grows like this, and this thing is depleted as you go on. But I think this is what I'm saying is correct. Psi 2 could be anything, and it represents a practical way of handling a complicated piece of the atom-atom interaction, besides the usual contact interaction, having to do with the internal structure of the atoms. Okay.
It might be interesting to think about this problem in a uniform potential, in a box. Because then, if you had two immiscible species, and you put them together in the box, they could be, one of them could be on the right and the other on the left, or could be on the top, could be on the bottom. There could be some very interesting patterns generated depending on relative scattering lengths. Has anybody thought of that?
No, we haven't, never did it in a box.
It's expensive energetically to have domains. So, but there might be, under certain conditions, the ratios of scattering length, there might be domains, there might be various patterns.
So you mean that the trap is making the effort to change the symmetry so as you have...
So in the system you have right now really depends on it being a harmonic trap. That's a very important component. As you say, the aspect ratio is important into the system. But in a box, it would be a different story. If it was a uniform potential, it wouldn't have that kind of, that parameter. So there's some symmetry in that system that would have to be broken, and how the immiscibility comes about might be interesting.
Yeah. then you must choose to be one side or the other. That's it. Okay, you can, in principle, you can try it. Thanks.
I see that you always have vortex in both components, right? Why, if the immiscibility is high, you know, so one doesn't work like a hardcore for the second piece, and then if I introduce rotation, I'm going to have the one that's outside with a giant vortex, the way we do in, you know, if I have a 2D condensate, I put a rotation and a hard core, I just generate a very high rotation vortex that stays there and cannot decay. Why that doesn't happen here?
In this case, we are rotating both. We are not rotating one.
Yeah, I know, but
we are rotating
still,
both.
the core works like a hard repulsion for the second piece, right?
We are rotating both. And in principle,
Oh, you're putting rotation in the whole system. So.
Yes, there's rotation in one species and rotation in the other species. It's not. Well, maybe thinking experimentally is easier to just rotate one of the species, to shine a laser and rotate, but we are rotating both.
Well, no, I think a possible situation will be a giant vortex. Maybe you have an individual vortex in the inner part, but then you have a giant vortex with more or less match the core of the second species. Why not possible?
I don't know. Why should be that?
Well,
this is the minimum energy
feeling
in the parameter. Maybe what you are saying that can be some set of parameters that you have vortices in one, more vortices in one species and less vortices in the other species. But there are some examples. Let's see here. You see here is different number of vortices in one system. Here is double core vortices in the other. But one interesting thing that whenever you have vortices in one, you must be the other one filled the space. There is filling. So here you have vortices and you have filling with the other species. You see, this is interesting. Whenever you have vortices, you see there is vortices here, and there is filling with the other species in these vortices. The other species occupy the space left for these vortices. But the number of vortices is different from one species to the other.
So,
anyway.
Just briefly addressing this point. So these would be the analogs of vortex bright solitons for contact interacting systems.
Sorry.
In contact interacting binary mixtures, there's this species called vortex bright solitons. This is a vortex where you fill the notch with a bright soliton, which actually can be a repulsively interacting species. You just call it a vortex bright soliton. So this is what you see over here, is it? The dipolarly interacting analog of it.
Yeah.
Okay.
Can I ask you one thing? Could you show us the phase diagram which appear on the way?
This or the other one?
Yes, the other one, probably the previous. Yes, this one. So when we made the calculation without the dipole-dipole interaction, we found several states which were degenerate. And is the degeneracy broken by introducing the dipole interaction in your case? We found several states which are degenerated.
What do you mean by degenerate?
The energy is almost the same. For example, without the dipole-dipole interaction. Yes, around here, vortex structure, vortex pair states or something like that. Yes, around here.
I don't know if we didn't look at to see if the energy doesn't change here. No, we didn't pay attention to this. We can check this, but we didn't pay attention if the energy is not changing here with the rotation. So you rotate and the energy doesn't change. It's strange.
Yeah, we found, for example, these states are very degenerated. Yeah.
You mean by fixed delta?
Yes, if we fix delta and very close to the unity.
Okay, very close to the unity, and
yes.
then you change you change the rotation. When
The-
you change the rotation, the energy should change. Should change. Once you include rotation, you change the energy. I don't see how can be degenerate anyway.
Okay, talk
Okay, we
later.
can
Yes,
discuss
okay,
this. We can
yes.
discuss this.
Any other questions or comments? Okay, so thank you very much.